So welcome to this session. As I explained, we will the first one Irving was presenting his work as a poster. So we are moving on with a second presentation from Franco Otaola about the optimization of periodic open cell structure reactors.
Thank you. Hello, everybody. Thanks for coming. So today I'm going to talk about the methodology and development and optimization of periodic cell structure reactors. First of all, to give a little bit of context, most of the chemical industry today uses catalysis in general, and in particular heterogeneous catalysis. It's used in the biggest industries of the world. And in general, we are today using an old type of reactors that they are packet bed reactors. Most of you, I hope they know, but it's a packet bed, so they have catalyst particles inside of it. And the main advantage of it is that it's really easy to fabricate and really easy to operate, but it has its own drawbacks. Like, for example, it has really high pressure drops, and it can have channeling and hotspots. One idea was you listen correctly? It's okay.
Oh.
Oh. So in the bibliography, it was suggested the structured reactors, and this type of reactor has a regular structure inside of them. And in particular, we got interested in two types: the monolith that has straight channels inside of the reactor. The main drawback of this type of reactor is that they doesn't have any diffusion in the radial direction, because each channel is separated from the others. And the foams that are another type of reactor, that it's a foam, generally a metallic or a ceramic one, that it has an irregular structure, better surface contact area, and high heat transfer conduction. And the idea is combine these two types of reactor by using additive manufacturing to create the periodic open cell structures. This type of structures has a regular form that it's repeated in the three-dimensional directions, sorry. And it has the benefits of the foams, where we have radial mixing, at the same time the regularity of the monolith. The main drawback or characteristic, it's not a drawback, it's something good. It's that, could you please mute everybody? Thank you. So it's that we can have different, these structures are composite in three different levels. The strut geometry, that it's going to repeat it to generate the unitary cell, and this unitary cell, it's going to be repeated in the three directions to generate the complete structures. As I mentioned, the thing is that we can play with each of these levels to generate different structures. So, for example, we can change the strut geometry and generate different unitary cells that it's going to have an impact in the final geometry, or we can use different unitary cells to have also an impact in this type of reactors. The thing is, our challenge today is understand this type of reactors and also arrive to know which one of them are the best for our application. Obviously, you are all CFD users. CFD, it's a good answer for this type of challenge. In particular, we interested ourselves in the pressure drop of the reactors and also in the dispersion inside the structure. The dispersion inside the reactor, it characterizes the dispersion flow, the deviation of the flow from the plug flow inside of the reactor. So it's described by the Peclet number. And when you have an ideal plug flow, you are going to have all the molecules that enter a reactor. It's going to spend the same time inside of it. In the contrary, in a real flow, when the Peclet is lower, some molecules, they are going to spend less time and some molecules more time. This is quite important because in a chemical reaction, you can have secondary reactions and undesired products. So the different geometries that we study, we have 3 different types of strat. We choose the cylindrical one. We have 6 different type of unitary cells. We choose the cubic and the octet. We have different sizes of the unitary cell, the unitary cell size, and the strut diameter. That we choose 3 different unitary cell strut size and cell size. And also we have 2 more parameters that they are the alpha and beta, that they are the angle in respect to the flow. This unitary cell can be rotated in the direction of the flow, and this is going to change the main geometry. And this one we choose 45 and 33.2. This is so the flow goes by the vertex of the cube in a cubic unitary cell. All the geometries were created by Salome, and the Salome, the generation of the geometry was created by giving these parameters, these different parameters that are going to use in Salome to create the geometry and also the surface mesh of the reactor. And this surface mesh, the STLs, as we call it normally, we use it to create the complete geometry of the reactor. The complete geometry is going to be 3 cells in height, 1 cell in wide, and with a constant length in the flow directions. So the simulated physics, as I told you, we were going to calculate the pressure drops that we used simple foam in a dimensionless configuration. Why? Because the reactors are really small. So when we are refining the mesh, we are going to finish with really small cell sizes. And for the dispersion inside the reactors, in CFD, there exist 3 different methods. The particle tracking, where we inject Lagrangian particles in the inlet of the reactor. The transport of a passive scalar, where we inject a passive scalar in the entrance of the reactor and we measure the concentration. And a third one that it's quite new, that it's called steady moment transport, where we calculate the different moments of age inside the reactor in a steady state. We choose the third approach because it gives us less information, but at the same time, it's a steady state simulation. So it's going to be faster and easy to do different iterations over the different geometries. So this is the equation that follows the steady moment transport, and we need to solve it for the first and second moment. And with the first and second moment, we are going to be able to calculate the Peclet number, that it's going to be the interstitial velocity inside the reactor divided sorry, 2 times the first moment divided by the central second moment. And from the Peclet number, we are going to be able to calculate the dispersion coefficient. So the first thing we did, it was a validation of this method, and we use the only theoretical result that they are from the dispersions, that it's the Taylor and Harris model, where we calculate and we can calculate the dispersion inside a straight circular tube, where the length it's 100 times the diameter of the tube. And we did the same thing, but by OpenFOAM, obviously. We obtained the validation of the method. The complete workflow, to summarize, it's going to be, we give the list of geometric parameters that we are going to give to Salome to generate the geometry. Then we are going to generate the 3D mesh and do the simulation of the different physics. We are going to extract the different interesting parameters. This is going to be done by OpenFOAM. This it's going to be in a loop created by a bash script. So it's going to change the different parameters as the simulations were done. And then we are going to analyze the results and generate a response surface. This is done by MATLAB and Python. So the first thing we did before doing the loop, optimization loop, was to see the grid independence of the results. So we did the same case at different meshing, at different block meshes sizes. And we stayed in the second most refined mesh, where it's only 0.5 difference to the next level, and it was 50 million cells of difference. So we had two, here are the main results, where we can see that the dispersion it's going to go up as the geometry is less porous. This is normal because it's a laminar flow inside the reactors. We are simulating really small velocities. But at the same time, we are going to increase the catalytic surface of the reactor, that can be quite interesting in chemical reactions. Here is the same, but for the other geometry. And as conclusions, we did a first approach of the complete workflow for the generation, studying of the different geometries. We are going to validate the experimental results in the box with experimental data. And the idea is, after adding new physics, such as chemical reactions or heat transfer, and depending of the different physics that we are going to simulate and what we are going to look for, we are going to create an objective function to minimize or maximize these parameters. And we are going to continue in different in the exploration of different geometries. Thank you.
Well, question.
Yes. Hello.
Very nice.
Thank you. Yes. They are exactly, they are, it's an scalar. Here I present this is the equation for the two moments. Actually, if you use n equal to 1, you are going to solve for the first moment, that it's quite easily to see physically what it means. It's going to be the average time that the molecule is going to spend inside of the reactor. And once you calculate the first moment, you can calculate the second one, because you are going to use it inside the equation for calculating.
Yeah. But on the equation, for convection, you have diffusion.
Yes.
I was expecting not to have diffusion in the equation, the second term or the first term on the right hand side.
Yes.
The diffusion like term. So it's kind that something can.
It's.
You have diffusion there.
Yes.
I was trying to figure out what would be the meaning of that diffusion. For instance, the part.
Yes, well, it's like in the case of the transport scalar, where you're going to have a diffusion, a molecular diffusion. It's not like the particle tracking where you have a discontinuous thing. Okay. Yes?
So thank you for a very interesting talk. I have one kind of follow-up question to the middle one. It's this is very interesting idea for these moments. But I would be interested. There is advection term. So how is this affected by numerical diffusion in your, because you go to the first moment, which has some numerical diffusion, you use it on the right hand side for the second moment computation, like double numerical diffusion.
Yes.
Remind you briefly.
Sorry. Yeah, to repeat the question. So your question was about the issue that I'm going to have numerical diffusion inside the moment because I'm using the first moment to calculation of the second one. And you are completely right. It's one issue that we had, especially at lower diffusion and molecular diffusions. We had a lot of trouble because even by, well, if you see here, when we were doing the independence of the meshing, you can see I went really refined to reduce it, and even it was not that it stopped at all. It was that we needed to stop at one moment because I was doing simulation of 700 gigas of RAM.
To make this model more efficient. Same processors, we are running this. This is not an overnight process.
Yeah, well, it's if you have a look at the difference in the error, even if we go a little bit less refined, it gives a small error in difference, and with 2 or 3 levels less of refinement, you have around 3 or 4% only of error, and it was all the simulation in 3 levels less. There are 2 days, and there are 18 simulations. The idea is to throw several hundred of combinations and leave it running.
2 days, 18 simulations, several hundreds.
Yes. Thank you. Any other question?
We have one chat.
Yes. Sorry. Hello, nice presentation. One question: did you try to compare the pressure drop through the structures with experimental data, if available? Actually, experimental data available, there's not a lot of them because most of these structures are used experimentally with gas flows. We did our simulations in liquid flows because we are working in experimental applications in flow chemistry, and we didn't find a lot of information about it. We are going to measure ourselves, so the experimental part it's going to be done by our laboratory.
More questions in the chat. So, speak again.
Okay.
Okay.
Good afternoon. My name is Lucie Kubíčková, and I would like to present you my work where I focus on methodology for topology optimization, where I utilize a hybrid fictitious domain-immersed boundary method. And at the very beginning, I will just introduce you what the topology optimization is. And I will start with a small illustrative example where just imagine a plane, where a plane is something you can, well, simulate. You can simulate the flow of the air flowing around it. And imagine you would like to optimize the fuel consumption of the plane. And you want to do it by modifying the wings. And before I go to the topology optimization, I will start with something more simple, because the most basic approach you can adopt is a sizing optimization, where you just modify the dimensions, the length and width of the wings. But you may, well, end up with that. It may not be, well, sufficient, just the sizing optimization. So you would like to do something more complex. And more complex optimization approach is a shape optimization, where you can modify the dimensions of the problem, but also the shape. But still, this may not be enough. And the most complex and the most general optimization approach is the topology optimization, where you optimize the dimensions and also the shape, but also the connectivity of the object. So you are able to create new holes in the object or new loops. And yeah, the topology optimization is the most general optimization approach, but also the most challenging one because of high dimensionality of the problem. And now to the topic of the presentation, how it's done in CFD. When you look in the literature, there are several methodologies proposed already, but they usually are based on this scheme where there is some optimization algorithm, which may be either some gradient-based technique or some stochastic method. And these algorithms are led to optimize parameters of a level set function based on which the component topology can be changed. And then the authors usually used immersed boundary method to construct a CFD model, and they somehow evaluate it using either a finite volume method or some lattice-Boltzmann method on surrogate models. And based on that, they evaluate optimization criteria and optimize the component. And you may notice that the gradient-based techniques are usually linked with the finite volume method, and the stochastic methods, which are usually more costly, are linked with the surrogate models or the lattice-Boltzmann method. In our methodology, we aim to create the methodology as robust as possible and as general as possible. So we used stochastic algorithms, concretely multi-objective evolutionary algorithms. And the main advantage is that they are able to find the global optimum of the optimization problem, but they need thousands of evaluations of the cost function. And also we didn't use a level set function because sometimes it may be not sufficient. And we used binary representation of the structure because it's a more straightforward way of representing it. And you have more control over the topology itself, but also it brings more dimensionality into the problem. Then, yeah, the CFD model, we used OpenFOAM, and we created it using the variation of a immersed boundary method, concretely hybrid fictitious domain immersed boundary method, in our own implementation in OpenFOAM work. Yes, and apart from this, the rest was done in Python. And I will present the methodology on a proof of concept optimization problem, where this optimization problem was a optimization of a diffuser, which was equipped as a part of an ejector, where ejector is a simple jet pump, where at the inlet there is high pressure liquid, which energy is utilized to entrain a low pressure liquid. And here the two liquids mix, and in the diffuser, the pressure energy is recovered. So the role of the diffuser is to recover pressure energy. So it has high influence on the overall energy efficiency of the device. So the goal of the optimization problem was to optimize the diffuser shape in order to enhance the energy efficiency. So, the efficiency we defined as this, as a ratio of a difference in pressure energy and reference kinetic energy. And we chose this optimization problem because we have already, conducted a optimization on it, but we used a less general optimization methodology where we did not conduct a topology optimization, but a kind of shape optimization where we worked with control points, and the result looked like this. And the main advantage of the less general methodology was that we could validate it on experiments because we cooperate with a group of experimentators. So we know that, it works. And this way we have a referential solution to the optimization problem, and we could compare the new methodology with it. And now to the methodology itself. First of all, let me just define the optimization problem. We define it as a multi-objective and multi-parametric. So there is some parameter space and some cost function that projects these parameter space onto an objective space. And the goal is to minimize the cost function. But there may be a problem with that the objectives may be anticorrelated. So they may not exist any single ideal solution to the optimization problem, but either a set of non-dominated solutions, and it's usually called a parity front. So a solution to the optimization problem is a parity front, and these problems can be solved using multi-objective evolutionary algorithms. Here is written briefly how they work, but I will illustrate it on this graph because these algorithms are based on random operators and they mimic the biological evolution. So they work with a population of individua, where one individuum is defined by a specific parameter vector and corresponding objective vector. And at the very beginning, the algorithm starts just from a randomly generated population. And what it does is that it picks pairs from the population randomly. Then it mixes their parametric vectors and creates offsprings. And like that, it has the population and offsprings, and he just chooses the best ones. So it's some kind of survival of the fittest. And like this, it can converge to the parity front and find the solution to the optimization problem. Yeah, and now to the problem itself, to the parametric space of the problem. As I said, we optimized shape of a diffuser. This is the default shape. Okay. And first of all, we just created a biggest acceptable shape. It just was this kind of cylinder. And then we adopted a axisymmetry approximation, since ejector is an axisymmetric device. In these simulations, we run in Lamere, so also the flow was axisymmetric. So our computational domain was just wedge mesh. And yeah, then came the binary representation. And how it works is that when you have the biggest acceptable shape, you can divide it into a finite number of topology cells. And then each cell can be filled either with material or void. And based on that, each cell can be assigned either 1 or 0. So like this, you can represent different diffuser shapes just using a binary representation matrix. And these matrices formed, were then reshaped into vectors, and these vectors form the parametric space of our optimization problem. But there we met our first problem, because not all the possible existing binary representation matrices define some reasonable diffuser shape. For example, where there was these floating chunks of material, there is unacceptable. Or when the diffuser is plugged with material, that's not good. Or where there were these closed cavities. So at the end, our parametric space was split into acceptable and unacceptable topologies. And due to that, The evaluation of the cost function also needed to be, well, different from the two groups. And for the acceptable shapes, we use the CFD. And for the unacceptable ones, we use just a penalty function, which is just a linear function, where these gammas are coefficients, hyperparameters of the methodology, and these n's are numbers. The first one refers to the number of cells that just float there inside, nothing. The other one is the number of cells that form closed cavities. And the last one is the number of columns the flow can't reach. So the evaluation of the cost function for the unacceptable shapes is quite fast and easy. And yeah, for the acceptable ones, it took long because we use CFD. And now to the CFD model itself. As I said, we used a axisymmetric mesh. It looked like this, just this part was much longer. And yeah, we used the hybrid fictitious domain-immersed boundary method, which allowed us to use just one single computational mesh for all the different shapes, because it works with a kind of solid phase indicator field, which we call lambda, and it gains values from 0 to 1. Well, cells with 0 are inside fluid, cells with 1 are inside material, and cells with value in between form the solid phase, fluid-solid interface. And also you may notice that we done some smoothing there. And then the flow inside those shapes was simulated using, well, these governing equations, which are for incompressible and isothermal flow of a Newtonian fluid. And they are almost standard Navier-Stokes equations, just with the added term from the immersed boundary method, which depends on the lambda field and simulates the force that need to act on a fluid to prevent it from entering the solid phase. Yeah, the boundary conditions are quite standard, and we simulated the simulations firstly in a laminar regime only. And based on the results of the CFD model, we could evaluate the energy efficiency of the shapes. Yeah, and the last thing about the methodology is optimization strategy. In the first step of the optimization strategy were preliminary optimization, the goal of which was to set the hyperparameters of the penalty function. And in this case, we were not yet interested in the results of a CFD model, so we here just used a modified cost function where the CFD model was just substituted with a simple ratio, where this was a number of cells with material. And then the preliminary optimizations, they started from a randomly generated population, and they were led to converge to a single acceptable shape. And we ran a couple of these and tried to set these gamma coefficients so that the optimization just converged in a reasonable time, which in our case was in a matter of minutes on a standard laptop. Second step of the optimization strategy were initial optimizations, the goal of which was to create a representative set of acceptable solutions. And they worked similarly to the preliminary optimizations. So like this, we created this representative set, and then we extended it by a few random individua, because it helps the algorithm to then explore the true parametric space. And from this extended set, we run the final optimization, which was the last step of the optimization strategy. And this final optimization used the CFD-based cost function, and its goal was to find the diffuser shape with highest energy efficiency. Yeah, and now to the results. Maybe? No? Okay, so, well, before any optimization could be conducted, we firstly needed to somehow verify our models. So we created a referential CFD model just using a shape conforming mesh, where we conducted a mesh resolution independence study. We observed the energy efficiency and ended up using mesh with cell scale about 0.5 millimeters. And then we recreated this shape using the immersed boundary method, and also compared several cell scales and compared the difference in the energy efficiency. And at the end, we used this this mesh because it was a good compromise between speed and accuracy. And then we followed our optimization strategy. And here are the results of the final optimization, where, as I said, it started from a predefined set of acceptable solutions with few random ones. And after 20 generations, it converged to something like this, where there were no more the random shapes, unacceptable shapes. And after 70 generations, it converged to something like this, where the shapes became looking very, very similar. And after a few generations later, it converged to just this one single acceptable shape. And when we look at the objective space, here is illustrated how the cost function changed during the generations. And there are also highlighted 3 significant shapes, where this one is the default shape. The second one is the shape acquired using the less general methodology, which was validated on experiments. And the last one is the result from the new methodology. So we may notice that when we look at the relative energy efficiency, you may notice that the reference methodology was able to find a diffuser shape with 60% higher energy efficiency, but the new methodology was able to outperform the old one and find a shape with 76% higher energy efficiency. So in conclusion, or to conclude, we created a robust and general methodology for topological optimization as it's a connection of genetic algorithms, CFD, and immerse boundary method. And next steps, well, our goal is to, or we would like to conduct the optimization also in, well, more turbulence regimes, but the problem is with turbulence is that you need finer mesh, and finer mesh takes more time to evaluate. And when we use genetic algorithms, there are thousands of evaluations of the cost function, so more computational time is not an option. So we would like to use runs, modeling, and cost function. So here are just some preliminary results when we operated in quite low Reynolds numbers, and we used, well, we just have some test case of a pipe, which we recreated using the immerse boundary method. And we were looking at the velocity profile along this line, where the black line is the result from the shape conforming mesh. The orange one is the result from the immerse boundary method without all functions, and the green one is the immerse boundary with full functions in our implementation. So there is a visible difference, but we are still working on the higher Reynolds numbers. That's all. Thank you for your attention.
Are there any questions? Yes, of course. Go ahead.
So we don't do the microphone thing?
No. I have to drag her. Then it's easier.
Okay.
If she.
So 2 questions, I think. So this HFDRB method, or immerse boundary method, I'm not familiar with it. How is that different to the standard approach, which is already in OpenFOAM, to just have this artificial porosity in the momentum equation? Because you said you also don't have a wall function in there.
Well, it is different. That's, you know,
briefly.
yes. There was a question how the immerse boundary method differs from the approach using the porous media. And well, the difference is that the interface is more resolved, and the boundary conditions is better defined. You can define a no-slip boundary condition using the immerse boundary method. Yeah, that's the difference.
And so then the reconstruction you did on the next slide is actually has this like these imperfection of the mesh. So I would guess if you would double the resolution or triple or whatever the resolution of the mesh, you will get something with like more continuous, right? But still with this like really blocky simulation, you get a decent improvement. Try to do some manipulation and have a smooth shape and then evaluate that.
Not yet, but well, this is just a proof of concept optimization problem, but we will consider it. Yeah.
Okay,
my question is with respect to the cost of the optimized geometry. I don't see how you account for how difficult it would be to manufacture or to fabricate the optimized shape? Is there a penalty associated with this? Is it easier to produce? This is less easy to produce?
Well,
Briefly, the question
okay, yeah, the question is about the fabrication of the optimal shape. And well, we cooperate with a group of experimentators, so we were talking about it with them, and they told us that, well, we could use 3D printing, and the only problem is with those shapes, for example, where there's just floating something or where it's plugged. So yeah, no other penalties were considered.
Sure, but I guess my question is, if you compare the result you got with this approach to the one that you used with your prior approach?
Not yet.
But when you showed the different results.
Well, the question was whether we compare the results to the referential methodology. And yes, we compare the simulations, and we know that the referential methodology is validated on experiments. So we assume that the new methodology is, well, better. Okay.
Chat. Yeah, I will read that now.
That was for the previous presentation, I guess, or that was your question.
Yes. Oh, sure. Then
You could answer.
no questions. I thought it gets unwrapped. Okay, so if there are no other questions, then.
Good afternoon. My name is Wagner. I'm a PhD student at University of Minho. I'm going to present the work that I have been working on for my PhD, together with my colleagues and also persons from the company that is involved in the project. João Romero, Francisco Alves, Bruno, and my supervisor, João Miguel Nóbrega. And the subject is the thickness distribution optimization for a blow molded part. So I divided this in motivation of the study, the background to you know more about, the methodology that we follow, some results and discussions, conclusions, and the future works. Okay. So the main motivation was the production and use of plastics that have been growing for the 50 years. So it's 1950 till now, it's like exponentially growing. And nowadays is about 13.6, 10 to the 6 tons per year of plastics. Then we have the main industry as the packaging industry, which is responsible for 42% of this use, and followed by construction with 19. Then, okay, from the packaging industry, we have the extrusion blow molding process, which is one of the major polymer processing of hollow plastic containers. And this industry is growing approximately to 3 to 5%. Okay. Keep on the motivation, we have the extrusion blow molding process that covers a wide range of parts with length scales from millimeters to meters. So we can have like some small, large, medium bottles, and also the fuel tank of the car is blow molded parted. We have those cases to store the tools that you open and close from plastic is blow molded as well. And we have the current pursuit for higher process efficiency, for saving materials use, and minimize produce waste requires to control the thickness distribution. So it will make sense for. So also the challenge for reducing the consumption of plastic, the computational modeling that have been used as an important tool for predicting and enhancing processing in several areas, also supporting the designing team to choose the best option to follow. And we have the OpenFOAM as an open source computational library tool that can help us. So OpenFOAM is a ready solution, no, but can it help? Yes, a lot. So since it's open source, we can have access to its code. Whatever it doesn't do, we can program to make it do. Then it also saves time because it connects with several other softwares for meshing, for post-processing. And the other thing it is important is the setup is text-based files. So it's highly automatized by scripting Python or Shell. So basically we want to use OpenFOAM as a computational tool to help the design team to give the solution for reduce the consumption of plastics of their company production. Okay, we have let's see. The first step for the extrusion blow molding is the extrusion step, where you have the polymer is a raw material, then they heat, it becomes a melt, then they push this through the gap formed between the two design. And okay, then it forms what they call person. So basically it's a tube of hot plastic tube. Then you have over there like the molds close and blocks one side of the hollow plastic and makes the other side open. So then air is blown and it inflates, pushing the person towards the mold walls to keep the format of the final part. Okay. So what we want to do, we want to model the process of clamping and inflating for now. And the approach that we want to do, it's a Lagrange approach. So basically we have our body and okay, this body is, we call the base, and it moves, rotates, translates, and stretches and deforms through the domain. So basically it's the mass, instead of volume of control, is the mass control of the system. Then we have the person, in which we want to simulate as a membrane. And we have the OpenFOAM finite area method for discretizing the geometry for the membrane. Okay. And then we also mesh it as triangular cells, as you can see in the right bottom. You have a sum of 5 times for the person as a circular shape. Okay. Then we implement linear and nonlinear constitutive models in order to predict the mechanical behavior of the person. And we follow a co-rotational formulation where you have like the coordinate system located with each cells of the person. Okay. Okay, the modes, comparing the stiffness between the person and the modes is very feasible to consider it's rigid, so it doesn't deform. And we just discretize, like we model as a STL, so standard triangulate surface format, but STL. And the contacts between the person and the mold is perfect sticked. So it doesn't have relative movement between them. So, okay. Then the mathematical model. We have the governing equations, the mass times acceleration equals the sum of the forces. Is a explicit approach. And for the constitutive model, we have like the stress tensor is equal times the stiffness tensors, double dot with the strain tensors. We have the fourth order stiffness tensors. Stiffness tensor is reduced to this 3x3 tensor do the membrane formulation. So it simplifies a lot our calculations. And we have a more complex, okay, this is, since we are dealing with large strains, large rotations, large translations, despite being linear, elastic is non-linear. They call hyperelastic. So it's the simplest hyperelastic model called Saint-Venant-Kirchhoff hyperelastic model. And the right is a viscoelastic one, in which the stress doesn't depend only on strains, but also with time. So it relaxes as the time goes, okay? And in order to obtain the internal force, we just do the stress tensor dot with the area vector. Okay, here we have two cells, finite area cells, triangular, and we have the membrane normal. We discretize the as face center, our domain, our unknowns, and also the thickness. So, and we have like the thickness with the yellow one, you can obtain like the area of the edge, okay? And okay, so with the membrane face normal, we can multiply by the pressure that it's being blown, and we obtain the force for the pressure. Then we have the gravitational acceleration vector pointing the direction of the gravitational force. And we also have the internal force, where it doesn't let these cells like move apart from each other. So there is no rupture simulation. To explain a little bit more the process, we have like an external solid. May I just, we have this part and this part is an external solid. And then you have an internal solid body that's placed aligned with the same axis from the outer and the inner, okay? And after this, we have that melt that flows through the gap formed between these two solids, concentric solids. Okay, so the inner solid moves upwards and downwards, making this gap thinner, smaller or bigger. Then this control how the thickness of a layer will be through the axial, as means the extrusion goes, okay? So for example, if we got this cut plane, we can have the thickness by the difference of the radius, like the yellow part. And if you got a little doubt, oh, it's very exaggerated here, just for explanation, okay? Then we have a thicker layer, okay? But and that was very important in order to make the groups of optimization. So this methodology, we use the optimization, we use for the optimization algorithm. We basically use the Pareson cells and we group them along its vertical axis, as you can see the layers from the top to the down. And each group has a initial thickness value. Then we perform the clamping and inflating simulations. After the inflating, we pick the same group of the cells from the beginning and calculate its final thickness. And we compare with the objective thickness. So as it differs, we correct the initial thickness. So then we have a loop process, okay? So to control, we have basically to set like the minimum axial value that, axial value from the person that you want to group the cells, and the maximum, and put the number of the groups that will be subdivided. After you have a layer, so a layer has a minimum and maximum Z value, then we loop through all the cells to split is as list of lists. So we have a list for group 1, which has some cells, list of the other, and so on. And how we do before, because if you see in here, for example, this group green in here, you cannot almost see in here. So it's Z in that time, but the other time it can moves anywhere. So we have to track this from where it was and how it terminates the deformations. To correct, so we have an average thickness. We also can put some weights on that. For example, if you want the algorithm to optimize more the middle section of the bottle or the bottom section of the bottle. And then you calculate that thickness difference and you correct the first. And we have some limits here. For example, you cannot have a negative thickness. And usually it's sense to make the thickness at least the same value as the final thickness. Imagine like it just touched the mold and didn't stretch. So it doesn't make sense have a thickness higher than the objective one. Okay, for case study, we decided to simulate this bottle with this 400 millimeters height and 250 diameter in the main section, and the next section as 50 millimeters, okay? And the target thickness is 0.9, more or less 0.2 millimeters, okay? Then, okay, so we start the comparison with a uniform thickness distribution as 4 millimeters. So like an extrusion without any movement relative between mandrel and die. And then we clamp and inflate and get this non-homogeneous thickness distribution. So with this and those groups that I mentioned, we optimize the initial values for the thickness for the comparison. Then we have now a non-uniform thickness distribution for the comparison and a more uniform, but still non-uniform thickness for the final bottle. After some iterative process, we obtain a final bottle with the objective thickness of 0.9, okay? And we should produce a comparison with this thickness distribution in order to obtain this final part, okay? And here is a simulation for the clamping and inflating steps for each simulation, okay? Okay. So to conclude my findings in this work, the computational framework is developed, and the simulation of blow molding process and automatic optimization have shown to be a powerful tool to aid the process design. The final part thickness reach a range of 0.9, more or less 0.175 millimeters for all the cells that belongs to the relevant surface. That's it, not consider the complete cells. Sorry, I didn't mention this, but whenever the cell is clumped, when the cell is clumped, it means like the plastic will be cut off and go back to the process. So we not leave the factory. It will be regrounded and remelt and reused to the construct a new part. So if you see here, the first layer, there is a blue region in which these cells were clumped and not considered to calculate this optimization. So, and okay. And an optimized part contains 14% less material than the optimized one, which is an important amount of material, especially for a large-scale production process. For future work, we are planning to perform the optimization of non-cylindrical shapes, for example, ovalized bottles, which you have to have a die extrusion design more different, and also different methods to group the cells in order to attain the objective thickness. For example, I could optimize each cell thickness based on its initial value and final value, but the answer that I would get is not used in practical for there is no machine to be built to obtain that comparison, you know? So and perform the simulation for the extrusion step, which is undergoing, and to extend the capability for the membrane in considering bending stiffness. Basically, the membrane has only planar stiffness. It allows to stretch, like resist to stretch, but do not resist to bending. So we want to do the same with shells, which have the bending stiffness. Okay. And I would like to thank the FCT and Search and MAC for supporting and helping us to perform the simulation. And these bottles are some bottles that we are also studying. And that's it. Thank you for your attention. Yeah.
So are there any questions? Yes, of course.
Okay, thank you for nice talk. I have two questions.
Okay.
First is, so you basically do solid mechanics in there, or which I completely misunderstood.
Okay, just he asked me if I did complete solid mechanics. Yes,
Yeah,
I did.
The formulation, it's for finite strength, it's updated Lagrangian, or?
Okay, he asked if my finite strength is updated Lagrangian. No, it's total Lagrangian for the linear, the hyperelastic. But we have the viscoelastic as an updated Lagrangian. But we are undergoing to this case, the high viscoelasticity didn't, if you notice, the clamp and inflate is very fast. So it doesn't let time to viscoelasticity be important as the extrusion phase. The extrusion phase is more or less 80% of the entire process cycle. So it's more relevant than.
Okay, thank you.
You're welcome.
The second question is related towards your optimization criteria. Did you consider also the final stress distribution in the bottle?
Okay, the question was if I consider the final stress for the bottle as to optimize, no? No, it's considered because you need the stress to predict where the cells will go. So when you stretch, it resists and can move there. If touch the wall before, it can stretch more, you know? So, but the stress limit is not my, how do I say, my problem. It's not because it's a melt. The polymer is between liquid and the solid. It's a melt. It's more, so it doesn't break. It doesn't. I don't have like limit stress to my problem. So basically, I just had to know the material final, the distribution of the material, in order to optimize my design and optimize the material distribution. So the stress was not a critical thing for my part. It can be for if breaks, but this is not covering in my studies yet.
Okay, thank you. I was asking because I guess that you created in a heated way. So the model goes in a heated way and then it cools down after being blown up. And after that, I would be afraid about the possibility of some residual stresses in the material.
Yes, there exists. Sorry. He asked about also after the mold closes and inflate, it cools down. And this can create a residual stress in the final part. And yes, this I didn't cover, but is the next studies as well. I think it is ongoing. But
very, very nice.
So thank you very much. So
Over there, let's see the chat. Okay. Yeah.
I don't know who. Okay, thank you.
Well, thank you.